So the next one is electric field due to continuous distribution of charge. Due to continuous distribution of charge. Till now you have learned electric field due to only a point charge, right? Now you have found out the electric field at a point due to a point charge. But what happens if you want to find out the electric field due to discharged body? And find out the electric field at this point P due to discharged body. Suppose this is a rod of length L which is placed at a distance A from this rod. 그러면 electric field at the point P will be 1 by 4 pi epsilon naught. Suppose this rod has a total charge Q. If you take Q by distance of this point P from the end of this is A. If you take like this, then that's wrong. Is it okay? You have to consider the entire rod, not just a point on the rod. Alright? Yeah. And what happens if you want to find out the electric field at this point due to discharged body? See? If you want to find out the electric field at this point due to this charged spherical body. This is what we are going to study here. So electric field at a point due to continuous distribution of charge. Alright? Very simple. We need some basics on integration, which we have learned during the introduction class of class 11. In class 11, before we started our syllabus, I have discussed some basics about integration, differentiation, okay, logarithms. So that things are going to be utilized over this. Okay, over here. So consider a uniformly distributed charged body, a rod of length L, having a charge Q. Alright? Now I want to find out the electric field at this point P, which is at the distance A from one end of the rod. Alright? Okay. So in order to find out the electric field at the point P, I need to place a test charge at the point P. Right? Is it okay? Yes. Now what I'm going to do is, I'm going to break this rod into small elements, each of length dx. Okay? It will not look like a square box. This is just one-dimensional line. This is just a line. Okay? 이거 라인 있다 쓰되. 아차. 이거 box 니시나 sheet 니시노지 시도나 line 있다 보나고. Total charge Q. This rod has total charge Q. Okay? The charge is uniformly distributed all over the length. And let's consider that the length of this rod is L. I want to find out the electric field at this point P, which is placed at the distance A from one end of the rod. Is it okay to you? Now what I'm going to do is, I'm going to divide this rod into small elements, into small lines, each of length dx, and having charge dq plus dq plus dq plus dq up to infinite times will give you q. To infinitely large times will give you Q, right? No? So consider one such element. Consider one such element. Okay? Consider a small element of this rod of length dx having charge dq. No? And let this point P be at a distance of x from P. Then from the relation of electric, what is the relation of electric field at a point due to a source charge Q? E is equal to 1 by 4 pi epsilon naught into Q by R square. I'm going to use this concept. So the electric field at this point P, due to this area element, will be given by, see, since this area element is this element dx, not area element, length element, this element has very infinitesimally small length dx. So it will have an infinitely small charge dq. Since it has infinitesimally small charge dq, it will produce an infinitesimally small electric field dE, right? So the electric field at point P due to small element dx of length dx is given by dE is equal to 1 by 4 pi epsilon naught into the charge dq upon square of the distance. Distance of P from this element is x. So x squared. We can say that this entire rod is made up of many small elements as this. Therefore, if I add the electric field at point P due to all those elements, that will give you the total electric field at point P. And it can be obtained by integrating this dE from, we'll consider such elements starting from here up to here. Now, element to yeti pra start korigen na iman tak hobo. So if we consider the element from here, then what is the distance of P from this element? E. And what is the, if we consider the last element, then what is the distance of this P from this element? L plus A. So we can obtain the total electric field at P by integrating this dE from x is equal to A to x is equal to A plus L. Are you getting me? When the element is here, distance of P from that element is A. They are small elements. The last element is here. When you are considering this element, then the distance of this P from this element is L plus A. So we'll integrate this dE from x is equal to A to x is equal to A plus L. A plus L. Are you getting me? So integration x is equal to A to x is equal to A plus L. What is your dE? 1 by 4 pi epsilon naught into dq upon x squared. 1 by 4 pi epsilon naught is constant. So constant is independent of this x here. So your total electric field E will be 1 by 4 pi epsilon naught. It comes out of the integration. And we integrate from x equal to A to x equal to A plus L dq upon x squared. What to do with this dq now? Is it correct? What to do with this dq now? This is a rod. The charge is uniformly distributed over its length. We have learned linear charge density. Linear charge density lambda is defined as Q upon L, total charge upon length of the rod. In this case, if you are considering a small area element, then the linear charge density will be given by dq upon dx. Right? If you're considering the small element was of length dx, having charge dq. So your linear charge density will become dq upon dx, correct? Okay. So therefore E will be 1 by 4 pi epsilon naught A to A plus L. Your dq, okay, so here your dq will be equal to lambda dx. So dq will become lambda dx upon x squared. Lambda is independent of x. So I can write 1 by 4 pi epsilon naught times lambda integration A to A plus L dx upon x squared. So 1 by 4 pi epsilon naught times lambda integration from A to A plus L x to the power minus 2 dx. Correct? Is this okay with you? I'm going to rub it out. Therefore, or this implies or your E will be 1 by 4 pi epsilon naught lambda. What is integration of x to the power n dx? Integration of x to the power n dx, x to the power n plus 1 upon n plus 1. It's plus some constant if it is definite, but here it's if it is indefinite integral we use constant, but here the limit is fixed, so it's definite integral, we know the limit, so we don't use any constant. So integration of x to the power n dx is x to the power n plus 1 upon n plus 1 between the limits a to a plus l. So 1 by 4 pi epsilon naught lambda x to the power minus 1 upon minus 1 from a to a plus l. Minus 1 is constant. So minus 1 by 4 pi epsilon naught times lambda. X to the power minus 1 means 1 by x. Integration from a to a plus l. Fine. So minus 1 by 4 pi epsilon naught lambda. 1 upon upper limit a plus l minus 1 upon lower limit a. Correct? We can take LCM here. If this is done, then I'm going to rub this out. So your E will be minus 1 by 4 pi epsilon naught lambda. If we take LCM, your LCM will be a plus lambda times a. I'm sorry, a plus l. This is a plus l. Then a plus L cancels, so a minus of a plus l, right? I'm taking LCM. This is a matter of jot now. LCM into lambda. A minus L upon a plus L times a. Minus a can get cancelled out. So we have minus 1 by 4 pi epsilon naught into lambda minus L upon a plus L times a. Minus minus plus 1 by 4 pi epsilon naught lambda L upon a plus L times a, which is the required expression for the electric field at a point due to a continuous distribution of charge. So I've discussed about the continuous distribution of charge in one dimension. You can further go for 2 dimension and 3 dimension using the same concept. Okay, you can try this now.